Welcome. In part 1 of chapter 17, we discussed carbohydrates, fats, and proteins. During part 2, we will talk about minerals, vitamins, and the rest of the essential molecules for nutrition. That concludes the three major types of food groups: carbohydrates, proteins, and fats. Next, we'll look at a variety of other important molecules for nutrition that fall outside of these three main food groups. Carbohydrates, fats, and proteins are all composed mostly of organic molecules. These are carbon-based molecules within our nutrition. Dietary minerals are the inorganic substances that are necessary for life. The bulk structural elements and macrominerals make up more than 99% of atoms in the body. But that last 1% is composed of some trace elements and ultra-trace elements that are still integral to proper function. In table 17.3, we can see all of the elements essential for life. Atoms like hydrogen, carbon, oxygen, and nitrogen are used to make fats, proteins, and carbohydrates. Macrominerals like sodium, potassium, and calcium are integral for neuronal function and can be obtained in a variety of different foods as well as within water. We also have a variety of other trace elements and ultra-trace elements that are necessary in small amounts for our body to function properly. Lack of some of these dietary minerals can have serious consequences. For example, iodine can lead to the lack of iodine can lead to a goiter in the throat, as depicted in this photo. Iodine is extremely important for our thyroid to properly function and produce a variety of hormones. There is one more set of organic molecules that are integral to nutrition, and these molecules are called vitamins. They are essential to our diet, but do not include proteins, fats, carbohydrates, or minerals. We can classify them into two different classifications based on their structure and their solubility. Fat-soluble molecules and vitamins are going to have many carbons and hydrogens, but lack oxygens and nitrogens. Water-soluble vitamins are going to have a much higher ratio of oxygens and nitrogens to carbons. We can take a look at these two vitamins present here, retinol and vitamin D2. Both of these vitamins are considered to be fat-soluble vitamins because they contain only one oxygen each. These are going to be able to dissolve into oil, but not dissolve into water. Our water-soluble vitamins have many oxygens and nitrogens in them. The oxygens and nitrogens allow for these molecules to hydrogen bond to water, and therefore the molecules themselves will be soluble in the water. In figure 17.4, there is a summary of some of the different vitamins. We have in the first column the name of the vitamin and whether it's fat soluble or water soluble, and then sources of the vitamin. What happens if our diet doesn't include some of these vitamins? Well, the deficiency symptoms can be shown in the final column on the right. Dietary fiber is important for digestion as well as maintaining colon function and helping control blood sugar and cholesterol levels. Fiber may be soluble or insoluble, where the insoluble fiber is cellulose. We discussed how our body lacks the ability to break the bonds within cellulose because we don't have the enzymes necessary to break the beta linkages. This fiber has some benefits even though we can't break the bonds within the molecule for energy. Water is also an essential part of our diet, and most of what we ingest. We looked at many reactions so far in this chapter, which are hydrolyzation reactions. This means that in order for those reactions to occur, water must be used to break the molecule apart. If you've ever wondered why a human can go almost a month without food, but only a few days without water, it's because in order to access all of the food that's stored in the body as fat and protein and muscle, water must be used to break the chemical bonds between those molecules. When the body is completely deprived of food for a period of time, it can go into a starvation mode. In this starvation mode, first glycogen is depleted, and then the body begins to metabolize its fat reserves. In order to obtain the energy from the fat reserves and break the chemical bonds within that fat, a different set of enzymes must be produced within the body. This leads to the body changing into a state of ketosis, as ketone bodies are released into the blood and urine. These are the byproducts of breaking down the fat. As ketosis occurs, acidosis can also occur because the blood pH level will drop. In this slide, we're looking at several of the ketone byproducts that occur during starvation and fasting. The functional group, highlighted in green, is the ketone, and in some of these ketones also exists the group highlighted in red, an acid. This acid has an acidic OH group, which can lead to a lowering of the pH in the blood. Food additives are substances that are added to food in order to change the properties. There's a variety of different reasons to use additives, but most commonly they're used for taste, they're used for increasing the lifespan of the food on the shelf, and they're also used for packaging. The most common additives that are added are sugar, salt, and corn syrup. Some additives are added to the food in order to improve the nutritional value of the food. For example, potassium iodide is added to salt in order to produce a source of iodide. Vitamin B is added to rice. Vitamin C is often added to fruit juices and other beverages. Vitamin D added to milk to prevent rickets, and vitamin A added to margarine. These are just a few examples of some of the additives that are used to enhance the nutrition of common foods. Many molecules have their own unique taste and smell. For example, vanillin, pictured in the top right here, is the chemical that's responsible for the smell of vanilla. If you've ever used vanilla in baking and gotten that strong smell, it's this molecule here. Diallyl disulfide is responsible for some of the flavor and smell of garlic. Often these chemicals are used as food additives in order to enhance the smell or flavor of a food. Sugar is a molecule that many people crave. There are many artificial sweeteners which have been made in order to replace this molecule and reduce the calorie load of certain foods and drinks. These molecules all have a different structure than ordinary table sugar. For example, sucralose has very similar structure to sucrose, except some of the oxygens are replaced with chlorines. This means that the body is unable to metabolize the sucralose, but we still obtain the taste. These artificial sweeteners have different levels of sweetness compared to sucrose. We see here sucrose has a relative sweetness of 1. If we were to look at aspartame, the relative sweetness is 180 times higher than sugar. This means that we need 180 times less aspartame to obtain the same level of sweetness as sugar. Another popular additive is monosodium glutamate, or MSG. MSG has a structure, shown on the right here, which is very similar to glutamic acid. Excessive MSG can be harmful. It should be consumed in responsible amounts. Another reason that chemicals are added to food is to prevent spoilage. By enhancing the shelf life of certain foods, we're able to export those foods to a much larger range of people. Some of these chemicals, shown on the right, are used to prevent spoilage from molds, yeasts, or bacteria. Sodium nitrate can be used to cure meats, and it gives the pink color to ham and hot dogs. This molecule is able to convert to nitrous acid in the stomach, which can react with amines and form carcinogenic nitrosamines. Carcinogens are any molecule that has the ability to cause cancer. Some additives are in the antioxidant class. The antioxidants are able to stop the formation of free radicals, or they're able to quench free radicals that already exist. Foods that contain fats can turn rancid over time due to the formation of these free radicals. So the antioxidants not only react with the free radicals to prevent their chain reaction from spoiling, but they also have therapeutic values once consumed, as they can fight free radicals within the body. Here are the structures of some fairly common antioxidants. One thing to note is that all of these molecules have a 6-carbon ring that is connected to OH groups. This is called a phenol. Many of these are in the class of polyphenols. Those are common antioxidants. Another aesthetic reason to add chemicals to different foods is to create certain pigments or colors. Here are a list of some of the most common food colorings that are used for orange, red, and yellow. Some of these food colorings have been banned because over time it's been found out that the chemicals are carcinogenic. Carcinogens exist in natural food as well as additives. There are carcinogens all around us, in the environment and in our foods. Some scientists estimate that we consume natural carcinogens at a rate of 10,000 more than the rate of synthetic carcinogens. Of the 5,000 deaths per year that are related to bacteria, viruses, and other parasites in food, very few of these are associated with the intentional use of food additives.